what he has given one small example, like in schools, we never used to take the notes, but when we are in the college, then we have to be very attentive. We have to listen, we have to write, and we have to understand. So, I mean, all the faculties, have to be. We have to coordinate all those kind of stuff. It's a new experience for them, and so I'm sure that things will be very, very fine. And so thank you very much. Thank you, Dr. Amrit, for giving this opportunity, and looking forward to have a wonderful day, 3 days ahead. Thank you very much.
Thank you, sir. Thank you, sir. Government General Degree College Singur is the youngest government college in the district of Hooghly, affiliated to the University of Burdwan, West Bengal. The college boasts of a dedicated and erudite faculty who strive to create a milieu in the college that is conducive to learning for students and teachers alike. Numerous academic projects, scholarly discussions, enrichment programs, organizing social and cultural events constitute the annual activity calendar of the college. Each faculty member is actively attached to modern research, and many of them are engaged in projects with notable research organizations across the country. With a view to merge culture and academics, the college seeks to enlighten each student with knowledge beyond the ordinary. Students who have already graduated from this institution hold their alma mater in high regard, not only because of what they have been able to learn here, but also because of what has made them into well-balanced individuals, spearheading the next generation towards a glorious tomorrow. Government General Degree College Singur will continue to engender such pioneers for the society in the days to come. The tireless efforts of our respected principal, sir, Professor Dr. Shantanu Chakraborty, ensure the smooth functioning of the entire college and involve all students in inquiry-based learning so that they may be dissuaded from learning by rote. May I now invite Professor Dr. Shantanu Chakraborty, sir, to kindly call the workshop open with your valuable address. Sir, please.
Thank you, Amrit. Am I audible?
Yes, sir.
Okay. Government General Degree College Singur, Hooghly of West Bengal, and Indian Association of Chemistry Teachers, Homi Bhabha Center for Science Education, Mumbai, with Rani Rashmani Green University, Tarakeshwar, Hooghly, West Bengal, welcome you to 3-day National Web Workshop on Chemistry. Am I audible?
Yes, sir. Yes, sir.
In chemistry orientation for UG and PG students. This type of orientation programs for the students are undoubtedly the pressing need of the time. A huge number of participants across the country have shown interest and have registered in this workshop. That is a clear indication for their urge to widen their thought processes in a subject like chemistry. We feel extremely blessed to have with us personalities like Professor Satyamurthy, former Director Aizer Mohali, Dr. Prabodh Choube, the former Senior General Manager and Head R&D Center BASF, and Dr. Gulshan Sheikh, Associate Professor and Vice Principal Academics, St. Xavier's College, Mumbai, Dr. Anupa Kumbkar, Associate Professor, Savitri Bhai Phule, Pune University, Dr. Sumon Dotto, Associate Professor, IIT Guwahati, and Dr. Nirjat Deshputre, Senior Technical Officer of Aizer Pune, as resource personnel of this workshop. I would like to thank Professor Dr. Prabhu, General Secretary, ACT, Professor Brijesh Pare, President, ACT, and Professor Ashutosh Ghosh, Honorable Vice Chancellor of Rani Rashmani Green University, for extending their support for such a wonderful academic endeavor. I would also like to thank Department of Chemistry, Government General Degree College Singur, for taking such an initiative to organize such an event in collaboration. Department of Chemistry, Government General Degree College Singur is committed to provide value-based science education to students coming from various socio-economic backgrounds across the state of West Bengal. The core objective of this virtual event is to provide the platform to the students for a fruitful scientific exchange with zero capital investment. and also to develop the scientific aptitude. I firmly believe that all the participants will be enriched by listening to our honorable speakers for the next 3 days, whom we have in our midst for this workshop. I extend my best wishes for all of them. Thank you very much.
Thank you, sir. Thank you very much. Now let us move to the technical session 1. All the resource personnel of this workshop have such an illustrious list of achievements that if we talk about their achievements alone, the entire duration of the workshop will be covered, but the list may not end. We have always known them to be extremely helpful towards students and dedicated to the service of education. They have always supported the student community with their unquestionable commitment and readiness to extend their help. We welcome you, our honorable speakers. Our first speaker for today is Professor N. Satyamurthy sir. Sir was the former founding director of Indian Institute of Scientific Education and Research, ISER, Mohali, and former professor of IIT Kanpur. Sir was the president of Chemical Research Society of India. Sir completed his BSc and MSc degrees from Annamalai University. Then Sir moved to the United States, where he obtained his PhD degree with Professor L.M. Ruff at Oklahoma State University in the year 1975. He further carried out postdoctoral research in Nobel laureate J.C. Polanyi's laboratory. After that, Sir joined the Indian Institute of Technology, Kanpur, as a lecturer in the year 1978. Sir has contributed in the field of theoretical chemistry, molecular reaction dynamics, and computational chemistry. Sir has received many national and international awards throughout his research career. They include the most coveted Shanti Sharup Bhatnagar Award in Chemical Science in the year 1990, Sir C.V. Raman Award by University Grants Commission in the year 1997, Silver Medal from Chemical Research Society of India, Bangalore in the year 2001, and FICCI Award from New Delhi in the year 2001, to name a few. His contribution in the life of students is unquestionable and indispensable. No student can ever say that they had to return empty-handed when they sought Sir's help. His dedication towards research and teaching is exemplary. Not only does he love the subject to the core, but also makes sure that his students share this love, and he ensures that this happens by constantly motivating them and disseminating the facets of the subject amongst his students as well as his colleagues. We have always known him to be extremely supportive to the student community with his commitment and sincerity. It is unfortunate that we could not arrange this program in the previous week, or else we could have celebrated Sir's birthday during the workshop. Belated happy birthday, Sir. Thank you for inspiring our generation. May I now request our beloved Sir to deliver the session. Over to you, Sir.
Thank you, Amrit. Can you hear me now?
Yes, sir. Yes, sir. Thank you, sir.
You have to let me share. Right, you are the host, right?
Yes, sir.
So can you allow me to share? You know, Amrit,
Yes.
there is somewhere it should say.
Yes, sir.
Can you see my slide? Not yet, no?
No, sir.
No. So can you guide me on this? I found out how to do it on Zoom. So
Yes, sir.
today
Yes,
I have
sir.
a
Yes, sir.
problem.
Sir, actually, in the Google Meet platform, you see that in the downward panel, the third one from the right, there is a calling tune type of symbol followed by three
Yeah.
dots, and then, sir, one upward directed arrow. The third one from right.
Third one, let me just try.
Yes, sir.
The third one from the right
Yes, sir.
has a set of people. Huh?
Yes, sir.
The upward arrow you mean? Press
Yes.
it now. Okay.
Yes, sir.
Okay. Your entire screen.
Yes, sir.
Yeah, I think I am getting there now. Are you able to see it?
No, sir, not yet, sir.
Oh, not yet. Okay. Sorry about that. So here it should share. Screen is cancelled. Screen. Let me try once
Yes,
more.
yes, no problem, sir. Sir,
See,
yes, sir.
I pressed this arrow.
Yes, sir.
It says your entire screen, a window, a tab.
Yes, sir.
I should do the entire screen, right? Or a window.
Yes, sir. A window.
Yeah, a window. And then what do I do?
Sir, if you click it on window, sir, then you can share the screen. Sir, if you face any problem, if you email me the PPT, then I can share it for you, sir.
No, but that is very big, isn't it? It's
Yes,
very
sir.
big. Maybe I should have sent it earlier.
Yes, sir.
Let me try one more time and.
No problem, sir.
Sir, I think sharing the screen is easiest. So when you go full
Yeah,
screen,
so can you
show
guide
everything.
me through it? Yeah.
Yes, so again the
It says
three dots,
yeah.
share screen.
Okay, 3 dots. Let me try that. Full screen. It just makes my screen full. My apologies. Normally, I've been using it without any difficulty.
So can you try sharing once more, going to the right bottom?
See, normally on the right bottom, you get a share sign. Nah?
No, here
But
there are 3 dots.
Yeah, 3 dots, yes.
You can please click there.
3 dots.
And then you will.
Yeah.
Then you will get the share screen in the middle. Then you will get the share screen.
Yeah, I don't see that. I see a whiteboard, change it full screen, change background, captions, report a problem, troubleshooting, settings.
Sir, you may try the upward directed arrow.
Yeah, upward directed arrow, there are 3 choices.
Yes.
Okay, entire screen, window, yeah.
Tab.
Entire screen, sir, please.
When I do the entire screen, yeah. And then I do the... but how do I respond? It's not accepting my response. That's the problem. Now let
Maybe
me
you have
try.
to select the screen. Yeah.
See, it says it does not allow me to screen. Okay, let me see if I can mail this to Amrit.
Yes, sir.
My apologies
No,
to
sir. No,
the
sir. No problem,
viewers.
sir.
Amrit?
Sir, have you emailed it to me?
Yeah, it's uploading. It's 40 megabytes.
Okay, sir.
It's
No
uploading
problem, sir.
slowly. Yeah, so I request the viewers to bear with us. Another few minutes we will.
Yes, sir. No problem, sir.
It's coming as a drive link. You have to download
Yes,
it.
sir.
Yeah. Yeah, Amrit,
Yes, sir. Yes, sir.
can you hear? Can you
Yes,
hear
sir.
me?
Yes, sir.
Yeah.
Yes, sir.
See, it is uploading. So without making people
Yes,
wait,
sir.
can I get started? And then after a few minutes,
Yes.
you can. We will see if the file has been sent.
Okay.
Well, first of all, I want to apologize
No
to
problem, sir. No problem, sir.
our audience for the
No
delay.
problem, sir.
It was completely unexpected because we have been using this technology most of the time it works, but today for some reason it is not working. When Amrit asked me to give this lecture, I readily agreed because now I would like to I'd like to talk about what goes into deciding the factors deciding rates of chemical reactions. Chemistry is all about bond breaking and bond forming. The question is, how fast can it take place? What is the mechanism for this process? Normally, we talk about elementary chemical reactions. By this, we are told at the high school level, at the college level, that elementary chemical reaction is something that cannot be made simpler than that. Right? Like in fundamental particles, you talk about elementary particles. It cannot be broken into other particles. That's where we were taught. We learned about protons, electrons, neutrons as elementary particles. But later on, we learned that these elementary particles are not so elementary. They're quite complex, and they could be made up of other particles. I don't have the competence to talk about them. Our high energy physics friends would talk about the composition of the elementary particles. Similarly, when it comes to elementary chemical reactions, what you normally think of as an elementary chemical reaction often could be made up of several steps. And each, what chemists call a step, could actually be a very complicated process. Once we have the slides working, I would like to show you that one of the simplest reactions that we could think of that people today talk about to solve the energy problem is to split water, get hydrogen and oxygen, and allow them to recombine in a fuel cell so that you can generate electricity, and the byproduct will be water. And then this water could be split further, and then you get hydrogen and oxygen. As long as you have the sun shining, this process can continue because there is no limit, there is plenty of water, there is plenty of sunshine. A friend of mine, a well-known chemist, used to say, good things in life are free. The examples he would quote are light, water, and air. Air is still free. Light may not be free all the time. It depends on where you live and what is the season. And water, we have been taking it as free until now, but slowly it is getting more and more expensive. And people talk about shortage of water in future. Now, so this simple process of hydrogen combining with oxygen is a very complicated process. If you look back at the history of chemical reactions, you go back more than 100 years. One of the simplest reactions that was thought of was between hydrogen and oxygen to give hydrogen iodide. This is called a Bodenstein reaction, Bodenstein mechanism. Bodenstein in 1899, which means 122 years ago, showed that hydrogen gas could combine with iodine vapor and form hydrogen iodide. And if you heat hydrogen iodide, it would decompose and give you back hydrogen gas and iodine vapor. What was remarkable was that in 1899, he could show this quantitatively. He could measure the rate of the reaction, and he could show that the rate was proportional to the concentration of hydrogen, which is partial pressure of hydrogen, and concentration of iodine, which is the partial pressure of iodine vapor. And the chemists would call this a second order reaction. And if it is elementary in true nature, it was thought it would take place exactly as it is written, that is H2 plus I2 giving 2HI. If the forward process is valid, then the reverse process also should take place. Two hydrogen iodide molecules should come together and form H2 plus I2. Until a few years ago, the NCERT textbook used to give this as an example of how an H2 molecule and an iodine molecule could come together and form HI, or HI2 HI could come together and form H2 and I2. They would even talk about an intermediate or a transition state, a trapezoidal geometry for this process. But more than 50 years ago, Sullivan, when we get the slides working, we will show you, Sullivan showed that this reaction is not that simple. And it's actually quite complicated. Let me see if, my slides are still loading up. I will send it to Amrit in another few minutes, then we will be able to go through them. What he envisaged was, what you think as iodine vapor is actually in equilibrium with iodine atoms, a small quantity, but a small quantity of iodine atom is enough to get the process started. So he said, if you actually measure the rate of a chemical reaction very carefully, you would find it is proportional to hydrogen molecule concentration, partial vapor pressure, partial pressure, and the square of iodine atoms. And of course, since iodine atom is in equilibrium with iodine molecules, there is an equilibrium constant that relates the iodine concentration, atom concentration with the molecule concentration. And you end up with a rate which is the same as what Bodenstein showed. In other words, he did not make a mistake in measuring the rate of the reaction. The measurement was correct, but the interpretation was not so correct. The reaction actually went through a little complicated process. It could involve what one would call a thermolecular process. In reality, as Amrit said, this is an orientation program for college students, entry-level students. I would like to emphasize most of the reactions that you come across are actually bimolecular. When people say it is unimolecular, often you would find that unimolecular reaction is preceded by a bimolecular process. When people say it is a thermolecular reaction, you would find invariably it is preceded by a bimolecular process. Even the so-called unimolecular reaction, you have to pump energy into the molecules. Enough energy for the molecule to break, to isomerize, or do something, or have a catalyst, or whatever. You influence it externally, that you find that truly unimolecular process is not truly unimolecular. It has more steps involved. So some of the simplest problems involve bimolecular processes, and this is what we want to talk about. Now, how do we determine the rates of chemical reactions? The simplest way is to treat atoms and molecules as hard spheres. Simple model. Two spheres, if they come in contact with each other, then they can undergo a chemical reaction. If you remember, I mentioned for a chemical reaction, either a bond has to break or a bond has to form, or both should take place. Minimum requirement is a bond breaking or a bond forming. So if you want to break a bond, you must provide enough energy to break it. If you want to form a bond, simply bringing two atoms together is not enough to form a bond, because if two atoms come together, just as they come, they will simply go back. Remember, these collisions are elastic. Energy is conserved. If they come together, they will fall apart unless there is an intermediate. The intermediate could be a solid surface, a liquid surface, or another atom or molecule in the gas phase, which takes away part of the energy, so that when the two species, when they come together, they are allowed to form a bond. Now, so in a simple way, you can think of two spheres coming and touching each other as a minimum requirement for a chemical reaction. On some other occasion, I would talk about, not today, we don't have time, talk about some processes where this hard sphere model fails because they don't have to come together. Even when they are far apart, you can have an electron transfer reaction. This is what happens when you burn sodium vapor in halogen gas and you form sodium chloride salts. Nature doesn't form that way. Nature forms sodium chloride. Today we know that we can extract it from the seawater. Now, how did the sodium chloride get into seawater? We do not know. How the elements were formed, that it's a big mystery. How they were formed in the stars, how the elements of hydrogen and helium were formed in the beginning of the universe. These are all topics by themselves that require a lot of time and discussion. So assuming a sodium and chlorine come together and sodium chloride is formed, then that process, it turns out, is preceded by an electron transfer process. In this case, the rate of a chemical reaction would be larger than what you expect from two spheres coming together and touching each other. All right. So for processes which are governed by collision, where the atoms or molecules have to come together, you require certain minimum energy for them to react. And this minimum energy, we can call it the activation energy. The activation energy itself, it looks like a very simple concept, but can be, it's not so simple and straightforward. When Arrhenius proposed the idea of an activation energy, he simply wrote K equal to AE to the power minus EA by RT to explain the rate of inversion of sucrose. Remember, this was more than 100 years ago. And when the question came, what is this activation energy? I learned in school, and I used to teach, that this is the minimum energy the molecules must possess in order for them to react. Now the question is, how do you get activation energy? You have learned in high school, +2, nowadays you learn. You plot log K versus 1 over T, and you get a straight line. But it turns out it is not so simple. There are many reactions for which you don't get a straight line. And even for the same reaction, as the temperature changes, the straight line can change slope. It need not remain a straight line. It can have a curvature. Activation energy need not be positive. It can actually turn negative. You would be surprised. You may find it difficult to believe that the activation energy can be negative. There are some reactions, particularly involving free radicals, where the activation energy is negative. In some sense, Arrhenius' equation was only a mechanism or method for compacting data. Today, people talk about large data, data science, large data. When you have a lot of data, how do you look at them? How do you compact them? How do you make sense out of them? In that sense, this is what Arrhenius did more than 100 years ago. He said, plot log K versus 1 over T, and you get a slope, and that gives you an idea of how fast or how slow the chemical reaction is taking place. But today, in the 21st century, even 100 years ago, people were not ready to accept it. They wanted to know as to why or how does the activation energy arise. Yeah, Amrit, I have sent the file to you. It's about 40 megabyte.
Okay, sir.
Moment you receive it, it has been sent from my computer. Moment you receive it, please share it with us.
Yes, sir.
Until then, I will go on with this discussion.
Okay, sir.
Now the question arises is, what is the meaning of this activation energy? About 90 years ago, or 95 years ago, a lot of development was taking place. Schrödinger discovered or announced his Schrödinger equation. Simultaneously, Heisenberg had announced his Heisenberg uncertainty principle. Simultaneously means, you have to look at it very carefully, look at the date, look at the year in which the sequence of events took place. But in 1925-26, Schrödinger wrote the Schrödinger equation. It turns out he first wrote the time-independent Schrödinger equation first, and then wrote the time-dependent Schrödinger equation. The time-independent Schrödinger equation deals with transition probability. What is the probability of a reactants transforming into products? But the probability is not enough for chemists. We need to know the rate. What is the speed with which reactants transform into products? Now, in order to solve this problem, even before Schrödinger, we knew how to solve classical equations of motion. After all, people knew from Galileo onwards, or even before Galileo, to follow the planetary motion, what we call the classical mechanics, Newtonian mechanics, you treat atoms and molecules as particles and solve classical equations. When you solve the classical equations of motion, if you remember the second law of Newton says force is equal to ma, you need to know the force. Force is a negative gradient of the potential. So to know the force, you need to know the potential. Now for atoms and for an object falling on Earth, we know what the potential is. It is the potential, the gravitational attraction. When apple fell on Newton's head, it was the gravitational pull that was responsible. Yeah, Amrit, now I can see it. Can you go full screen?
Yes, sir. Yes.
Can you see my pointer? No. You cannot see my pointer.
Yes.
Okay. So since I will not be able to operate, I request you to go ahead and go to the next slide.
Yes, definitely. Sir.
Yeah. Go to the next slide. Yeah, so this is what I was talking about. An elementary chemical reaction, the standard experiment, at least when we were in school, was the teacher would dissolve zinc in dilute hydrochloric acid, collect hydrogen gas, and then when it turn it upside down, and then put a little glowing splinter, and you hear a pop sound, and then our teacher would tell us that hydrogen is burning. So we used to look at it with a great awe. And we didn't know what questions to ask, but we believed the teacher. What we have collected was hydrogen gas, and it was burning in air. And of course, we knew it was burning because you got that very characteristic blue flame. And then if you look carefully, there would be some amount of water condensed. So it turns out that is not so simple, as I mentioned a little while ago. It goes through several steps. First thing is the hydrogen molecule should break. It forms a hydrogen atom. The hydrogen atom combines with oxygen molecules, gives you this peroxy radical. And then there is a sequence of processes, several elementary steps before the reaction is completed, before you get water molecule. The next slide. Amrit? Yeah. So here is the Bodenstein reaction I was talking about. H2 plus I2 forming hydrogen iodide. And both the forward and the backward processes are second order processes. At one time when I studied in college, we used to think of them as bimolecular processes. But as I said, Sullivan showed that it is not a bimolecular process. It actually goes through a intermolecular process. Now, there are interesting experiments that are carried out. Anderson in Yale University crossed a molecule of hydrogen iodide and a deuterium iodide in a cross-beam experiment and showed that hydrogen deuteride was not formed, showing that the reaction does not proceed through the molecular mechanism. Go to the next slide. This is a classic reaction where a hydrogen molecule and deuterium molecule could in principle form two hydrogen deuteride. Now one can do theoretical calculations and show that this reaction faces a large barrier. What it means is that you have to provide a lot of energy to break a hydrogen molecule or a deuterium molecule and form hydrogen deuteride. Now, you go on to the next slide, please. Some of you might have studied about Woodward-Hoffmann rules in organic chemistry. Definitely at the final year BSc, MSc level, you would hear about it. The Woodward-Hoffmann rule tells you if you bring two ethylene molecules, they will not form cyclobutene. What they say is that a 2 plus 2 addition is not allowed. However, if you have an ethylene molecule and if you have a 1,3-butadiene, they could come together and form cyclohexene. So 4 plus 2 addition is allowed. Next slide, please. There is a reason as to why this 2 plus 2 addition does not take place. Unfortunately, that itself takes several minutes, so we will not have time to talk about it. I want you to only, the take-home message is that a 2 plus 2 reaction has a problem. It is what is called a symmetry forbidden process. Next slide. Now, when you look at ortho and para hydrogen, see, we study about carbon allotropes. When we were students, we studied about diamond and graphite. But 1985-86, we learned that Smalley showed that you can form Buckminster fullerene. So then we learned that there is another form of allotrope. So in principle, you can have several forms of allotropes. You can have, we studied several forms, 2 forms, 3 forms of allotropes of phosphorus. You can have different allotropes of sulfur to allotropes of oxygen. You can have oxygen and ozone. Ozone is an allotrope of oxygen. It turns out even hydrogen can be present in the form of ortho and para. What is the difference between the two? I hope you can see. I have marked in red color. If the 2 nuclei of hydrogen molecule have parallel spin, that would be ortho. If the two protons have the same spin, the spins are added, then the total spin is equal to 1. I'm talking about a nuclear spin. This is ortho. The 2 new protons can also have opposite spins, in which case it is para. Now, what is the consequence of it? Element-wise, both are hydrogen molecules. They are made up of same hydrogen atoms. But because of the nuclear spin, once they are formed as an ortho or para, it will remain that way unless you can break the bond and reform it. You can follow up the consequence. If the 2 nuclei have the same parallel spin, then you need to turn it around, turn the other one. So unfortunately, one of them is white. Let me show you here. Yeah. So if the 2 spins are parallel, if you want to make them anti-parallel, you have to break the bond and form the hydrogen molecule. So for this ortho-para conversion, once that is formed, ortho will remain ortho. Once that is formed, para will remain para. Next slide, please. As early as 1930, Farkas was the name of the person who was able to measure the conversion of para-hydrogen into ortho-hydrogen. And what was important was that he measured the activation energy to be 5.5 kcal per mole, and the temperature was about 800 to 1000 Kelvin. The question came, if you want to break a hydrogen molecule, you must spend a lot of energy, 109 kcal per mole. If you're used to thinking in terms of a kilojoules multiplied by 4.18, that is the kilojoules you have. But the activation energy is not even 10%. So how does nature do this magic of converting a hydrogen molecule where the 2 nuclei had parallel spin into having anti-parallel spin without breaking the bond? It turns out this could be rationalized. Next slide. This is about activation energy we have already talked about. It is a 5.5 kcal per mole. And remember, there are 2 ways of remembering activation energy. One is to say it is a minimum energy that the molecule must possess in order for the reaction to take place. And that is not 100% correct statement. You can make another statement. Activation energy is simply a measure of compacting data. Plot log K versus 1 over T, and you get a straight line, measure the slope. This is what is called a phenomenological approach. You observe a phenomenon and come up with a certain measurable. This case is activation energy is the measurable. But now you must analyze the phenomenon, interpret whatever you have measured, and try to understand the process. Now let us go to the next slide. So how does this reaction take place without breaking the bond? Remember, this experiment was done in 1930. Around that time, I told you about Schrodinger's equation came 1925-26. In another lecture organized by Amrit and Dr. Brijesh Pare and so on, I had talked about chemical bond. At that time, I had mentioned, you have learned about valence bond theory. Heitler and London gave the valence bond theory and gave a formula for determining the bond strength of a hydrogen molecule. Next slide, please. Now, this is calculating the rate constant. If you know the size of two spheres, you can calculate the rate constant by measuring the size of the spheres and the energy they must require in terms of activation energy, and you can calculate the rate. If you do the calculation, it turns out you get 90 times 10 to the power minus 16 centimeter cube per second. Amrit, can you show your pointer at the 90 times 10 to the power minus 16 centimeter cube per second? Yeah. But Farkas determined, you go two line below that. Schulz and Leroy 1965 determined to be 2 times 10 to the power minus 16 centimeter cube. In other words, what is measured in the laboratory is about 45 times smaller than what is expected based on the hard sphere model. What this tells you is that when they come together and collide, there is something more required. Not every collision is going to lead to reaction. Not having 5.5 kcal per mole is not enough to guarantee a reaction. If you know, this is like, I don't know if you know about buying shares. Just because you have money, it doesn't mean that you can buy the shares. I think now there is a share that was opened yesterday. I saw Zomato. Just because you apply, it doesn't mean you are going to get it. If there are enough bidders, some of them will get it, some of them will not get it. So if there are enough collisions, some of the collisions will be successful, some of the collisions will not be successful. What governs them is the intermolecular forces. What people did was, once Heitler and London in 1927 showed that you could describe the properties of a hydrogen molecule, London, one of the two co-authors, wrote down the equation, no proof, nothing. You know, this is like the mathematician, they give you the conjecture. So he wrote down the London equation and said this should be the potential for 3 hydrogen atoms. Next slide, please. Amrit, can you show me the next slide, please? Yeah, they are trying to talk about the activated complex theory. Next slide. This is the London equation. So based on the London equation, London, Eyring and Polanyi, they used the London equation and constructed the potential energy surface. Remember, this was 1931. What was important was that there was a concept of a potential energy surface, forces that determine the rates of chemical reactions. Next slide. This is the London equation. Amrit, if you can show the first equation, V equal to, Q, sum of the Qi, and then there are square root of things inside. The Q is called the Coulomb integral. The J is called the exchange integral. Based on the next equation, which was given by Heitler and London, based on the second equation, the first equation was written. It was not derived at that time. It was only in 1935 that the equation could be derived by Slater, saying under what conditions it is valid. But sometimes, you may have an approximate idea and you can still carry on with it. And that is where great people come in. The next slide. This is the idea of a potential energy surface. You plot potential energy as a function of the distance of the incoming atom and as a function of the outgoing atom. Amrit, you have to guide us through with your arrow from the reactants HH2 to the product H2H. Okay. So when you guide, so basically a chemical reaction amounts to riding on this potential energy surface. So what they thought was, if you could roll a ball that or a marble or a football, it will go from one side to another side on this hilly terrain. This is like any other hills, except that this is a potential energy hills, there are potential energy valleys. One valley is the reactant, other valley is the product. Let us go to the next slide. Now, I was chief editor of Resonance for 3 years, 2018, 19, and 20. January 2018, Resonance carried this cover page, where and the picture you see is that of Michael Polanyi, how he and Eyring envisage the chemical reaction taking place on the potential energy surface. The next slide. What they did at that time was very simple, conceptually very simple. When a diatomic molecule sits there and oscillates, you can equivalently describe this two-particle motion by an equivalent one-particle motion. This is what happens in a harmonic oscillator. You don't use the individual masses, but use a reduced mass. They said, can we do something like that for a three-particle problem? And they came up with an equation where they could show the motion of one particle on this surface. What you see here, the hilly terrain I showed you a moment ago, is the cuts of it, what are called the potential energy contours. You are used to seeing geodesic maps. When you look at the map of India, you see there are hills, there are mountains, and then there are valleys, and then, of course, there are plateaus. So the heights and depths are shown. So here you see each line connects all the points having the same potential energy value. So each line on this is a potential energy contour. From the right side where you have a reactance, you have to come closer and then move to the top. From right side, lower side, you move up and then go to the top left. That is how the chemical reaction takes place. Now, they didn't have computers. They did not know how to solve the equations of motion. They said, look, if we knew the potential energy surface, which they had an approximate idea, if we could somehow solve the classical equation of motion, we can follow this motion. Now still, so there is only a dream, there's only a concept where they showed in principle, this is what you need to do, solve the equations of motion and look at the process transforming from reactants to products. This was by Eyring and Polanyi. This was in Berlin. Eyring went back to United States and wrote his famous paper, Activated Complex Theory. He actually called the absolute theory of reaction rates. Looking back 190 years later, 85 years later, it looks somewhat silly that he could think of it as an absolute theory of reaction rates. There's nothing absolute about it. It was actually an approximation. This approximation is based on a fundamental concept. Let us go to the next slide. This is the modern depiction of the potential energy surface. This was drawn in 1973. Actually, 1973, the graphics are not so good. This, one of my colleagues in Hyderabad plotted for me using today's computer technology, but it gives you a similar potential energy surface. The basic idea has remained the same. Quantitatively, things have changed a lot. The barrier for the reaction has changed slightly, but the basic idea remains the same. Next one. So the basic idea is that you think of a transition state. You start from the reactants, you go to the product. Somewhere along the line, the reactant transform into products. They go through a critical configuration called a transition state. What Eyring did was, he said, look, if I know the properties of the transition state, I can calculate the partition function for the transition state. I take a ratio of the partition function for the transition state to the partition function for the reactants, and that would give me the rate constant. It was not exact, but it was an approximate idea. Incidentally, when Saha gave his ionization equation, the famous Saha equation, where he could determine the temperature of a star using Saha ionization equation. In the same issue of resonance, Shantanu Dattagupta, the founder director of IISER Kolkata, wrote a paper how independently 10 years earlier, that without calling it transition state, he looked at the partition function for the ion species and came up with the ionization formula, which could tell the temperature of the stars. People would argue that Saha should have gotten to say is that what was envisaged here as a transition state was also independently in a different context, and the astrophysics thought of to determine rate of a reaction. It's a revolutionary idea because you are using equilibrium properties to determine something which is not in equilibrium. Next slide, please. Amrit, next slide, please. Yeah, so here is the transition state. I have a few slides. They are all saying the same thing again and again. So let us quickly go through them because we lost some time. Next slide. Amrit, next slide, please. Yeah, so here is a simple question. Somewhere on the left is a reactant, somewhere on the right is a product. Where is this line? It could be drawn anywhere, right? I have put lots of question marks there. You need something to say that is the transition state. Next one. Yeah, so here I have symbolically written. I learned how to, if you look at a face, a characteristic of a face, you need two eyes, a nose, and a mouth. And the curvature of the mouth can actually depict your mood. On the left side, you see it is a sad mood. On the right side, you see it's a happy mood. Somewhere in between, you just draw a horizontal one. So based on the curvature, you can say whether the person in this cartoon is happy or unhappy. As a chemist, I have chosen forming the product is a happy state of mind. And you go through the neutral state of mind, and that is called the activated complex, also called transition state, and that is the top of the barrier. So anything that is on the left side must come up to the top of the barrier. Once it reaches the top of the barrier, it is a point of no return. It goes down the hill to form the products. So what we need to do, transform the problem of determining reaction rates into the problem of determining rate of going downhill once you reach the saddle point. I'm going to show you some more slides to illustrate the idea of a saddle. Go to the next slide, please. Next slide. Go to the next one. Yeah, we'll go. Yeah, go on. One more. Yeah, this is the, just go back. Amrit, one more. Back. See, here is a concept of the same three-dimensional potential energy surface. On the right-hand side, the products could be higher in energy, lower in energy, or equal in energy. You can have an endothermic reaction, you can have an exothermic reaction. Doesn't matter what the reaction is, the reactants must go through the transition state to go to the products. Next slide shows you a cut of the surface. Next slide shows you a slice of the surface. So here is an important slide. Here the same potential energy contours are shown, and from the right side you have A plus BC, and you follow the dashed line. It comes through the cross point here. That is the saddle point, and you go over to the products. It's the same thing said repeatedly to reinforce the concept to you. The next one. Next slide. So this is the picture that you learn in high school. The vertical scale is very simple, potential energy. The horizontal scale, the x-axis, reaction coordinate. The teacher very rarely tells you what the reaction coordinate is. It is something on the left, it is reactant, something on the right is the product, something in between is the activated complex or transition state theory, and you can define the reaction coordinate. Sometimes it is defined as the minimum energy path. You follow the point of lowest energy at every point and then come out on the product side. That's a minimum energy path. Some people would call it a steepest descent. If you go to the top of the barrier and you let a ball roll, one side will roll to the product, another side will roll to the reactant. So if you connect the two, that becomes the reaction path. Now these are all how you determine it is actually mathematical details. We don't have time to talk about them. The next slide. Here is a picture of a saddle. When I was a student, first time learning saddle, I could not understand what is the meaning of a saddle, but all you need to do is to look at the saddle on the back of a horse. Then I was wondering as to how does the name come from. It turns out the one that next to the horse you see is a mountain. Apparently in England, in Scotland, this mountain is called a saddle. That is how what is on the back of the horse is called a saddle. Next slide shows you the saddle in our own country. So when we had an opportunity to go to Siachen glaciers, throughout the journey from Leh in Ladakh to Siachen glaciers where our army is posted, and on the way you see so many saddles. You see this hilly terrain, there are minima, and in a mutually orthogonal direction, there is a maximum. So here is one representative sample. How many shots can you make? We need only one to illustrate the point. Here you can see the saddle in Siachen glaciers. Next one. So now we can talk about the mathematics of determining the saddle point. You can determine the rate of a chemical reaction. All that involves, we don't have time. It's a course by itself. One has to give several lectures, taking each idea into the logical follow-up. Next one. Next one. Amrit, go to the next slide. Yeah, so here is an example of a potential energy surface for an exothermic reaction. Amrit, if we can guide them from the reactants to the products, they will be able to appreciate how the shape changes. You start from F plus H2 on the left side. You go up and you go horizontally down. And then there is a small barrier here. That's about a 1 kcal per mole. And then you go all the way downhill. So if you reach the critical configuration, and after that it is all the way downhill, that is how an exothermic reaction takes place. Now go to the next slide. All you need to do is to reverse it. Now you start from the bottom of the valley here on the left side. Now you climb up. Amrit, you can show with an arrow how you climb from the bottom of the valley all the way uphill and then go over to the products. And you see that's a critical configuration. You go over to the products. So for exothermic reaction, you go downhill. For endothermic reaction, you go uphill. And that is the idea. So you also learned this in college. Next slide. And if it is an endothermic reaction, the saddle point resembles the reactants. And if it is an endothermic reaction, the saddle point resembles the products. Here is an endothermic reaction. It is an ion molecule reaction, a helium atom colliding with an H2 plus, giving rise to helium H plus plus H. Next slide. So you can, and this is for a little more complicated reaction. This was the case of H atom combining with the water molecule, an oxygen atom, or whatever. You can think of an atom combining, reacting with a water molecule, and you have 4 atoms coming together, and then they fall apart. So you can extend this to more complex reactions. Is the basic essence I want to convey here. Next slide. So based on this idea, so far I talked about Father Polanyi, Michael Polanyi, and Eyring, who gave the idea of a transition state and how they said you could, in principle, determine the rate of a reaction. This was a son Polanyi, 1960 approximately, 30 years later, where he showed that if it is exothermic reaction and if the saddle point is in the entry channel, then translation is helpful. And if it is endothermic reaction, the converse is true. For endothermic reaction, vibration is helpful. Now, how did he arrive at this conclusion? It was very simple. If you go downhill, it is not just going downhill. While going downhill, you rattle. In other words, the product becomes vibrationally excited. If you go forward and it is getting rattled, which means for climbing up the mountain in the reverse direction, you must rattle around and move up. And rattling is equivalent to vibration. The simple idea he demonstrated in the next slide. Yeah, go to the next slide. Go on. Yeah, here, this is an important slide made in 1960 approximately, where he measured experimentally how much of the HCl molecule, and a hydrogen atom collides with the chlorine molecule, form hydrogen chloride molecule, how much of it is vibrationally excited and how much of it is rotationally excited. Most of the energy goes into product vibration. And he argued, with the help of a friend, that by following the principle of microscopic reversibility, that means anything that goes forward must traverse the path in the same way in the reverse direction. I used to tell my daughter, she used to watch Mr. India movie those days. The new generation may not know this movie, where Anil Kapoor tells Sridevi, "Yahi seedhi upar jati hai, wahi seedhi niche aati hai." It is a staircase that takes you upstairs, same staircase that brings you downstairs. That is essentially a cinematographic way of illustrating principle of microscopic reversibility. Next slide. Yeah, go on. Next slide. He demonstrated for a bunch of endothermic reactions that if you provide energy in the form of vibration, the reaction takes place readily. Next slide. Yeah, here somebody else demonstrated that if you vibrationally excite the molecule, the reaction rate is faster. So it became very clear by late 1960s and early 70s, vibration helps reaction. How about if you excite the molecule rotationally? Next slide. Shows you just because you are putting energy doesn't mean the reaction will go faster. If you make the molecule rotate faster and faster, the reaction doesn't increase faster. It actually slows down. You could argue because if the molecule is rotating, the incoming atom is not able to participate in the reaction and form the products. That's one of the simplest ways of explaining why rotational excitation is not helpful for reaction. Now, what is it that I have tried to convey here? I have tried to convey to you that there is an important fundamental concept of a transition state, something through which the reactants go through to form products. If we could identify the transition state, as early as 1935, Eyring and Polanyi had shown that you could make an estimate of the reaction rate. As years went by, San Polanyi, Gian Polanyi, and a few others showed that in an exothermic reaction, energy is released as vibration. This is a fundamental basis for forming lasers. For forming lasers, you must have molecules which are electronically excited if you want visible laser. If it is vibrationally excited, you can form infrared laser. As a matter of fact, if a lot of chemical reactions can take place and a lot of molecules form vibrationally excited, and if they all emit light coherently, come down simultaneously, you would have a chemical laser. You can now run the movie backwards. You can use lasers, infrared lasers, to make vibrationally hot molecules and make reactions go faster. But people were not happy. They wanted to somehow capture the image of the transition state. When I started my career in IIT Kanpur, I used to say that you cannot capture the transition state because it doesn't live long enough. Now, I was silly because how do you capture an image? All you need is a shutter speed. If your camera shutter can open and close fast enough, you can capture any event. Nowadays, I can watch my grandchild jumping up and down or moving around, and I can capture it on the iPhone, and then I run it back again and again. So it became very simple and straightforward because today the technology allows you. Same thing happened in the late 1970s. People were wondering, can we not capture the transition state? The answer came, yes, you can, provided your shutter speed is fast enough. So we are going to skip a few slides and go directly to the idea. Yeah. So this, go on. Go on. Yeah. So here is the slide. Just go back. Yeah. This was the idea, Ahmed Zoil. He said, if you could have a clock which can measure at femtosecond, 10 to the power minus 15 seconds, then it is like a movie. You run a movie in the olden days, movies were made by making several shots and then running the shots at fast enough, 40 frames or 60 frames a second. Of course, you can run it slower, you can run it faster. A typical, that's how Walt Disney cartoons were made. They were to draw Mickey Mouse and Minnie Mouse and draw pictures and take pictures each one by one and then run them. That's how the cartoons were made. So Ahmed Zoil showed conceptually that you can watch a chemical reaction taking place in real time, in real space, and record it. He actually, just before he passed away, he wrote a book titled 4D Microscopy. And if you look at an issue of Resonance where we had given a description about Ahmed Zoil and his contribution, you would get the idea of 4D microscopy. What is 4D microscopy? 3-dimension space and 1-dimension time. So in 4 dimensions, you observe chemical reaction as it takes place. As a matter of fact, he wanted to record in real time unzipping of a DNA double helix. And of course, if he had done it, he was hoping that he would get a Nobel Prize, but that did not happen in his lifetime, But he and his group and others have made substantial progress in recording chemical reactions in real time. Next few slides, let us go through. Next slide. Here is an example. When you do a photochemistry, if you shine light, molecule gets electronically excited and it dissociates. It's a photodissociation. He showed that it takes place on the order of several femtoseconds. Next. Now, these are illustrations. We are going to skip all of them because we have run out of time. Next one. Amrut, we'll just go through the slides quickly. Just go on. I'll tell you when to stop. Yeah, go on. Yeah. So now go back to the previous slide. Yeah. So Ahmed Zoil showed that femtosecond is the time scale in which bonds break and bonds form. When I say femtosecond, it doesn't have to be 1 femtosecond. It could be order of tens or hundreds of femtoseconds in which a chemical reaction takes place. So about 10 years ago, we thought that was the end of it. Chemistry will stop there, and after that it is all physics. And when people discovered attoseconds, chemists initially thought nothing much will come out of an attosecond. But chemists were wrong. Because what you need to do now is to look at you ask a different question. What happens in an attosecond? Attosecond is 10 to the power minus 18 seconds. We talked about Heisenberg uncertainty principle in the earlier part of the talk. There is an uncertainty principle relating time and energy. Delta E, delta T is equal to h bar. If you shrink the time, then the energy gets spread out, which means a chemical reaction can take place not just from one electronic state, but from several electronic states. It gets more complicated. In other words, an elementary chemical reaction, which we wanted to simplify more and more and more, then you reach the fundamental atomic, molecular, electronic level, it gets complicated. If you improve the time resolution beyond femtosecond to attoseconds. Now, next question, next slide. Now it is up to you. If I have excited you about the complexity of elementary chemical reactions, and if you could tell somebody, today's lecture was all about transition state, how the concept was formulated, how the concept led to determining rates of chemical reactions, and how eventually people went about recording the spectrum of a transition state for a chemical reaction. And Ahmadzweil and others could accomplish it in the femtosecond time scale. If you could remember these a few points, then you have got the benefit of attending my lecture. Thank you. If you have any questions, I will be happy to answer. Amrut, you can coordinate if anybody has any questions.
Yes. Anybody has any question?
If you're feeling shy to ask, then I have given you my email address. You can send me the question, because sometimes I find that students write to me because they are a little shy of asking in public. I must say you must not hesitate to ask.
Yes, sir is asking for any questions. Do you have any query? Do you have any question? Anyone? Thank you, sir. Thank you, sir, for your wonderful lecture. We have learned so many things. Sir, you basically reminded us of the great scientist, Professor Robert Burns Woodward, whose lectures at the University of Harvard would carry on into night, and students would sit transfixed listening to him speak. It would have been wonderful if we would have been able to listen to you for a longer time. Thank you, sir.
Wow. But then you see, Woodward was Woodward.
Yes,
for
sir.
Satyamurthy, 1 hour is their time limit. I'm glad after we got the slides going that the internet was stable, because in the beginning we had a lot of problems.
No problem, sir. No problem.
I must thank you and others, organizers and the audience for being patient during this entire.
No problem, sir. Sir, actually we are extremely privileged to have you. Sir, please take care of your health. Thank you, sir, for inspiring our generation.
Yeah.
We are very much indebted to you, sir.
Since this is being, I think it was being recorded, isn't it?
Yes, sir. Yes, sir. Actually, YouTube recording is there. I have already shared the YouTube link among the participants who have joined our WhatsApp group. Actually, sir, near about 1,400 participants are there. And sir, I have created several WhatsApp group, and sir, I have shared the YouTube link.
Wonderful. So let them listen to it, and if they have questions, let them write to me. Yeah. Thank you once again, and thanks to everybody.
Thank you, sir. Thank you, sir. Please accept our regards. Thank you.
Shall I leave now?
Okay, sir. Please take care
Thank
of
you.
your health.
Thank you.
Act- Actually, our speakers are so eloquent and mesmerizing that we do not want to let them go. We want to continue listening to them and learn more and more things from them. However, unfortunately, since we have a limited time, we may not be able to accommodate questions from too many participants. Thank you for everything. The second speaker of today's session is Dr. Shumona Datta Madam. Dr. Shumona Datta Madam is an associate professor in the Department of Chemistry at the Indian Institute of Technology, Guwahati. Madam pursued doctoral work at the Indian Association for the Cultivation of Science, IACS, Kolkata, where she studied the theoretical aspects of nonlinear dynamics of spatially extended systems. Later, she worked at the Florida State University, USA as a postdoctoral research associate, where she started doing experiments with chemical reactions that displayed nonlinear phenomena. Her current focus of study at IIT Guwahati are the dynamics of spiral and scroll waves and their control in both experiments and theory, aimed at understanding the workings of the cardiac system. Apart from teaching and research, Shumona Madam is involved with different outreach activities and loves talking about science to the interested. She is especially passionate about popularizing science and mathematics among the school and college students. May I now request respected Madam to deliver the session. Over to you, ma'am.
Thank you, Professor Mitra. Very good evening to you and to everyone. My regards to Professor Pade, Professor Ghosh, and Professor Chakrabarti. And great congratulations to Professor Mitra, especially because of organizing such a beautiful workshop in this scenario, in this situation when people are home. We still get a chance to meet each other and to discuss science. And there is a very huge variety of flavors that you have organized from people. And I'm sure it will be a very enthralling experience for the students and whoever else is listening to these talks. It was a great pleasure and honor to listen to Professor Satyamurthy. So he is a stalwart in the field, but the way he has talked about the very basics of an entire subject is exceptional. And I'm also personally thankful to him because he kind of gave a very good starting point from where I will begin, because I am going to talk more about the relation of chemistry to other sciences, to the natural sciences, and to the understanding of nature. And I was a little worried that I'm not really talking a lot about chemistry, but it is nice that he has already talked a lot about chemical kinetics, and that is the basic tool or the major tool that we will be using to understand a little bit of thermodynamics. I'm not going to talk, as I said, dear students, about a lot of chemistry. I'll be talking about how we use chemistry as a tool and how chemistry links to the other sciences like physics, biology, geology, mathematics, and all the other subjects. So it is my earnest request. I would be very happy if people please raise your hands. You see, there is a raise hand icon, and you can please ask your questions when I'm speaking or at the end. That will be really enthralling because I'll be speaking about different things. And because I'm not going to go into the details of the chemistry, I would also ask anybody who is interested to learn more or know more to contact me at my email address, which I will be giving at the end. Okay. So I begin with my slides. I hope this works this time. Okay. Okay.
Yes, ma'am.
Yeah.
Yes, ma'am.
So, as I said, I promised that I would talk about heart attacks and what has chemistry got to do with that. We will try to understand that, and about pattern formation in nature. So, when we look up all around us, even as a child, we are really interested and enthralled to look at the different structures, the shapes, the designs that nature has to show us. So here we see some clouds, the formation in clouds. We always many times try to find different shapes in the clouds, right? So how does these form? These are stalactite and stalagmite structures that are formed in caves. There are several such caves in the Meghalaya region of our country, and also somewhere in the Himalayas. Many of you might have seen. You can see in patterns that are formed in the leaves and vegetation, patterns in the wings of birds, in mushrooms, and especially fish. Yes, fish skins have a plethora of different kinds of designs. Looks like some painter sat down and took different colors in a palette and painted them out. And what about butterflies, right? Even a very small child is amazed to look at butterflies that sit on the flowers. So how does these different patterns, the spots, the stripes, the colors, how do they emerge? And the royal animals, the Bengal tiger, the zebra, the leopard, the deer, some have stripes, some have spots. And did you know that a zebra, just like our fingerprint, is unique for every human? Similarly, the stripes on a zebra is unique to an animal. No two zebra in the world will have the same stripes. So those are patterns that remain with an individual or on the skin of animals, or that we can see in nature. Then there are other kinds of patterns that are more dynamic, that changes with time. Many of you have seen birds flock like a V they form, right? This aerodynamics, that it helps them fly. And then there are these very minute organisms. In this case, I show you a virus, which is known as the tobacco mosaic virus, and the colony of the virus, they arrange themselves in the form of a helix. Then other than the birds that fly in a particular congregation, there are also these monarch butterflies, who go across thousands of miles. So 2,000 miles means around 5,000, 4,000, 5,000 kilometers they go during a year. For one flight, they travel that much to go from the cold areas to the warm areas of Mexico. So they have a kind of GPS in the system, and they know how to fly together. We have seen shoals of fish. Small fishes act like a big fish to scare off, the bigger fishes. And another synchronization, or a pattern as I might call it, is the fireflies. So if you are from a rural area, try to look and find whether the fireflies sometimes flash on and off in unison. This is a unique phenomenon. This does not happen all throughout the year. It only happens in certain times when in the evening as it starts, you would expect to see only random flashing fireflies. But as time goes ahead, you will see that they flash in unison, flash on and off, as if it was a big, unique, single organism. Now, the questions of why these forms, how they do, they are many, right? Why is there so much symmetry everywhere we look? How does an organism have such a beautiful skin pattern when it starts from a single cell? It has all these complicated organs within and these beautiful patterns without. So how is it possible? How do these birds, fishes, and these butterflies know their way, right? How do they know that they have to arrange like this? See, all these questions come to our minds. And in order to understand them, we need to have some models that will be easy to understand. So other than mathematical models or theoretical models, just like Professor Satyamurthy said, we will see some equations which will help us understand. There are also some laboratory models, and some chemical systems act as beautiful laboratory models to show this kind of pattern formation. So these are some examples. The top is one chemical system where you see different kinds of spots and stripes. The middle frame again shows you another chemical reaction where you can see different kinds of patterns and different kinds of orientation of the patterns to give you different designs. And the last one is a chemical system where the patterns are all kind of circular, but when you look at it when you focus on it or zoom on in it, you will see that the way that the patterns are formed, they are unique, right? One is kind of a hexagon kind of structure, the other is completely circular, and all these different kinds. Now, here I am giving you examples of two chemical reactions along with the reactants. The first one on the top left is the thiourea, iodate, and sulfite system. So this system gives us beautiful patterns. Depending on the way we mix the chemicals, you can either get spots or stripes or a mixture of spot and stripes. You can see the similarity to the skin patterns of the animals that we saw earlier, right? And then you come down on the right and you can here see CIMA reaction. That's the chloride iodide malonic acid reaction. So here you can see spots and stripes in the same reaction occurring out of the reactants. The spots, again, they are very much like the leopard or the spots on the fish skin, and the stripes look like the stripes on the zebra or our fingerprint, right? So now all these patterns, I'm continually saying they are Turing patterns. So what is that? Well, before going to that, I would like you to think back once and realize that biology too is chemistry. Everything that is happening in biology is due to the molecules that are there, right? Everything follows the chemical rules, follows the kinetics, the thermodynamics. And the patterns that are seen are nothing but some chemicals that gives colors that are arranged in different forms. So you have to remember that. So this is one particular fish. So this is an experiment done by Professor Kondo in Japan. So they do excellent work on this field, and the field is known as morphogenesis. So this is a term that was coined by Turing. So I'll tell you soon who he is. Before that, please look at the fish. You can see that the fish has some stripes, and in the stripes there is some kind of a pitchfork kind of design. The lower panel shows you mathematical diffusion. So you take kinetic equations like we take in kinetics, right? And they solved it. And the lower ones are solution of the mathematical equations. And the top ones are actual pictures of a living fish at 10, 12, and 13 months of age. And you can see the pattern that looked forked like that. The pattern moved to the shoulder of the fish. And finally, there was no such bifurcation anymore. And you could see only parallel lines. So this is the change in the design with time. So the person who is responsible to give this term of morphogenesis and try to explain the similarity in the different structures that we have seen across systems is Professor Alan Turing, who was a mathematician, and he was a great one at that. You might have heard about the Turing machine, which is the first version of computers. Okay, so patterns in the cloud or patterns on the skin of a fish could be explained by his theory. This is one interesting offshoot, and I would like to share it with you. This is the Turing-Murray theory. Professor Murray is another mathematical biologist, and together he said that an animal with a spotted body can have striped tail, but an animal with a striped body will never have spotted tail. So if you go and look at the animals, or if you open up the internet and look at different animals and even lizards, right, reptiles, you'll be able to see that an animal that has a striped tail might have a spotted body sometimes. But if it has a spotted tail, then the body will surely be spotted. So how did they come upon this? Well, it's an observation to say that this is what is going to happen. But how does the differential equations come in here? So they come in because they said, you see the tail is much narrower than the body, the rest of the skin, right? So this narrow space, it can happen that the spots can get, so there is a spot and you make it small area. You can turn it around and it touches each other and becomes a stripe. That is possible, but vice versa is not possible, okay? So this is a thing that you keep in your mind whenever you see about an animal with spot or stripes. Have a look at its tail. So this is another experiment by Professor Kondo, and I would like to show you how the patterns change or occur or form in a tiny mouse. So the A is day 0, and each of these panels from top to bottom is a 30-day period. So you can see that the mouse at its birth was completely kind of dark, black, right? And then something changes near its nose, it becomes a little white, and then kind of the whole mouse becomes white, and then again it turns to black, and then it turns to white, but this time the white is not complete. It's a particular patch on the back. And then again, it turns black. The white turns black and the black turns white. Just keep looking. Then you will see why I'm showing you this. And then as the process goes, you will see finally at the end of 240 days, the mouse has a beautiful black and white patch or stripes on its body. Okay. So this is how nature behaves. Now I will tell you about a chemical reaction. And this is a very famous chemical reaction known as the Belousov-Zabotinsky reaction. So it is a mixture of very simple chemicals. The particular picture I am showing you can be produced by adding sodium bromate, peroine, sulfuric acid, and malonic acid. You will just need these 4 chemicals, and all are available in an undergraduate laboratory. So you can try this out when you go back to your college or universities. Okay, so this person, Boris Belousov, was trying to find an inorganic counterpart of the Krebs cycle. You have read about Krebs cycle? So he was trying to do that using inorganic chemicals. And he ended up finding that the color of the solution changed from one color. So particularly he started with cerium instead of heroin, and he saw that it oscillated between yellow and colorless. And then he put it on a petri dish, and then he saw these beautiful waves forming. And he tried to publish his work, but sadly, he could not do so. People didn't believe him. They thought he was making some error in either setting up the chemicals, the reaction, or something, because they thought it was going. Yes? Rasamri? Am I audible?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Heard a noise. I'm sorry. Yeah. So Professor Belousov found this and he wanted to publish this, but people believed that he was going against the reaction, or the finding was going against the second law of thermodynamics. Why? Because we believe that all reactions are all reactions are going towards equilibrium. And what do we see in equilibrium? Once it reaches equilibrium, there is no change to be seen, right? There are microscopic changes, but the rate of the forward reaction and of the backward reaction becomes equal. So how can the color come back again? So sadly, Belousov died an unhappy man. This often happens in science when you come up with something very new, something that people did not expect, then they may not take kindly to it and may not always welcome you with open hands. But then in order to find something which is extraordinary against that flow, it is necessary that you keep your mind's eye open along with your physical eyes, and only then you will come across this beautiful phenomena. And that is what nature does. Nature does not know what is the second law of thermodynamics. It just will go as it wishes. And finally, another professor, Professor Anatol Zabotinsky, he changed the chemicals a little bit, and instead of yellow and white, he used ferroin. And now you can see how the whole solution which is being stirred is going from orange to blue and orange to blue. So this is something that cannot be wrong, right? You can see that it is happening. And again, this is oscillating. These are called oscillatory reactions. So what happens when we put it on a petri dish? You can see there are spontaneous formation of waves. Of course, depends on the recipe that you're using, but you can form such a recipe where these waves are formed by themselves and they keep on going with time. They don't die, right? It is kind of like a living system. It's kind of like a pacemaker, as if somebody is sitting there and putting stones on this solution, right? So it's going on, and these are they are known as target waves, target patterns. So again, scientists were baffled. They could not explain until there was somebody who tried to look out of the ordinary. He said that systems did not go against the second law of thermodynamics, but they were systems that are far from equilibrium. So these systems have not reached equilibrium yet. And it's true that when it reaches the equilibrium, you will not be able to see any change. But these systems are far from equilibrium. So if you think about any living creature, our body, take for example, right, we have so many chemical reactions going on in our body, and they are nowhere close to equilibrium. Because if we are at equilibrium, we will be dead. Only after we are dead, the reactions will slowly move to equilibrium, and then there will be no more change. But all living things mostly are far from equilibrium. And most of these natural phenomena are very interesting when they are far from equilibrium. So reaction diffusion systems are the ones that I'm going to talk to you about, and they are far from equilibrium. When they are far from equilibrium, they behave as excitable media. So what is this excitable media? So I showed you the skins on the patterns, right? On the skins, I showed you patterns. I showed you this reaction, and then I will show you the heart too. So in all these cases, if I pass a signal, it will go without damping. So if you think about throwing a stone in a pool of water, the waves are going to dampen after a while. So that is not excitable. It will be excitable only if the waves reach the end of the pool without dampening. Okay. So another important criteria of an excitable media, or rather its quality, is after one signal passes, it requires some period to rest, or it is called the rest period or refractory period before another signal can pass. So that is very important, and I will show you how and when it is important. So what is this phenomena of far from equilibrium? So I'm again thankful to Professor Satyamurthy. He talked to you about the saddle, right? So I can think of a mountain where we have valleys and crests. So if I have a ball sitting up there, so depending on the initial condition, though it's leaning a little to the left, I'm sorry, it should have been. So let's say it starts moving on the right side. So it will come down, and it is possible, if the energy is not too much, that it might stop there a bit. And then it will fall again and stop there a bit, and fall again and stop there a bit before it comes there. And once it is there, it will require a lot of energy to move it up. But in all the small crests that it fell into, those could be local equilibrium, right? Around which you might see different changes. And once it reaches the lowest position, which is the global equilibrium, of course, we are not going to see any change unless we give a lot of energy from outside. So this is the phenomena of out of equilibrium. And the person who dared to look at something which was out of the ordinary was Professor Ilya Prigogine. And he won the Nobel Prize in Chemistry in 1977. And he wrote a book with a funny title. He said, Order Out of Chaos. So even Einstein had a statement to make about this, that everything is chaotic, but there is an order beneath it, right? So going back to the BZ reaction, or the Belousov-Zhabotinsky reaction, as Professor Satyamurthy made it easy by talking about a lot of simple chemical reactions and also complicated ones. You might have read your hydrogen-bromine reactions. Those are has many steps, right? Intermediate steps. So I'm writing the overall reaction here in this step, where you have bromate, you have malonic acid, you have H+, and you are getting bromomalonic acid, water, and carbon dioxide. Okay, so this occurs in the presence of a catalyst, and the common catalyst, we have used ferroin here. You know, ferroin is orange in color. You might have used it for your salt analysis, and the Fe3+ counterpart of it is blue in color. That is, ferrine is blue in color. So this redox indicator gives a beautiful color change. We can also use cerium sulfate that will oscillate between white or colorless and yellow. And ruthenium is also used, that helps in, it's basically sensitive to light. Okay. So one interesting thing that happens in this mechanism, I'm not showing the entire mechanism, it's quite complicated. If you want, it is available in Wikipedia, Scholarpedia, everywhere. You can have a look. But two elementary reactions in that I'm just choosing. And you can see HbRO2 is giving us BRO dot minus, BRO dot, BRO2 dot, and this radical in the presence of the catalyst NH plus is again giving us 2 molecules of HbRO2. So if you see, one molecule of bromous acid is giving us 2 molecules of bromous acid. So this is giving rise to autocatalysis, and this autocatalysis is actually taking the cycle forward. So if you remember your hydrogen bromine reaction, some cycle was continued with the free radical. Yes, free radicals are very important here. And you might have studied in your radioactivity, right? Where you got nuclear reactions, where you got 3 neutrons from 1 neutron, right? So that takes forward the reaction, the chain. And this autocatalysis is a very important step here. And this Belousov-Zapotinsky reaction, that is why gives the oscillation that we see. And the oscillation is not of the malonic acid slowly disappears as it goes into carbon dioxide and water. But the ferroin, that is the catalyst, that oscillates between the reduce and the oxidize phase. And that is the color that we see. Now, this Belousov-Zapotinsky reaction works electrical waves in the heart. Okay, the heart has some electrical waves, and that is what actually enables the heart to pump the blood. So the heart squeezes and contracts and relaxes, contracts and relaxes. So consider the small red dot here. Okay, that is like a heart cell. So if you look at the potential across the cell, which we plot here, you will see that the potential was kind of very negative. It rises up suddenly as the wave comes and slowly relaxes back. So that is known as an axial potential. So the action potential, which we have plotted here below, if you see that what has the relation to chemistry, right? What is happening in the cell actually? What is the signal? So when phase 0 is when it rises suddenly, sodium plus enters the cell. So a depolarization is occurring. And then phase 2, when it starts relaxing, the calcium 2 plus enters the cell and the contraction begins. And in the phase 3, the potassium exits the cell. So repolarization occurs. So the sodium and potassium ions are very important. And nowadays you can hear a lot of senior people, they have problem with sodium potassium imbalance. So that you can understand is very important because it will affect directly the heart and how the muscles or the cells in the heart, they contract and relax, right? And the whole heart is made of several such cells. And so together they make the heart pump the blood. So this is the shape of the heart in simple forms. It has 2 upper chambers known as the atria and 2 lower chambers known as the ventricles. And on the right corner is the sinoatrial node. This is where the pacemaker cells stay. And they are the ones that are responsible for giving off this initial signal. And the wave that passes through the heart goes undeterred. And so the heart is an excitable system. So a regular person's heart beats from anywhere from 60 to 90 per minute in the resting situation. And in a minute, the body or the blood that goes through the heart is 5 liters of blood. Okay, the heart can pump in and out 5 liters of blood. So you can understand So you can understand if there is some problem to this pumping, if something happens to the heart and the pumping is disrupted, then fresh blood will not flow to all the organs of the body, and we will have a scarcity of oxygen in the different parts, and that will be a huge problem. Okay, if there is no oxygen to the brain for a very little time, it can create damage that will be simply you cannot make up that damage, right? So cardiovascular disease, which are different in kinds, are the leading cause of death all over the world. This is a very old statistics, but you can have a look at any new statistics and you will find that this is really a serious problem. So what are the causes of heart disease? Of course, a person can have coronary heart disease, that is the blockage of the coronary artery, right? We know that. There could be stroke, where a blood clot can suddenly happen. There can be weak pumping. The heart can be weak to begin with, or with age, it may become weak and the pumping will become weak. But then there is a fourth kind of a heart disease, which is basically the cardiac arrest or heart attack that we say. That can happen in a very healthy individual at any time. And that is known as cardiac arrhythmia in its very simple form. So what is arrhythmia? I showed you the heart beats with a rhythm. So whenever the rhythm is disrupted, it is called arrhythmia. Okay, it can be slow heartbeats known as bradycardia or fast heartbeats known as tachycardia. So today we are going to mainly look at tachycardia. That is the increase of heart rate beyond 100 beats per minute in the resting. You can jump and run and it will go up a little bit. But if it just happens without any reason, then there is a problem. And these can lead to very serious conditions. Let us see how. So if you go to the doctor for any heart checkup, they will do an ECG of the heart. And many of you might have seen an ECG. So below here is a small panel of ECG. You can see some sharp peaks and some smaller peaks. So this is the exact nature of the peak. There is a small P peak with a QRS peak and a T peak. So the P wave is basically the excitation of the atria. That is the top part. You can see the left side, the heart is beating, and the right side, the wave is forming. So I'm making a 1:1 connection between the two, okay? So the excitation of the atria is the P wave, the QRS is the excitation of the ventricles, and the T wave is the relaxation of the ventricles. So since the ventricles are larger, so it's a bigger peak or a more sharp peak, okay? So these are the problems that can happen. What if there is a tachyarrhythmia or tachycardia, that is fast heartbeats in the atria, okay? So you see the atria here, there are some waves that looks like going round and round, and it is beating much faster than the ventricles. So what you expect, there will be many P peaks between two QRS waves. So many P waves. So this condition is not life-threatening to begin with and can be easily solved also. But it can move on to fibrillation. So what is happening here? You can see many waves that are very fast. The heartbeat that was supposed to be somewhere below 100 beats per minute in the atrial flutter has become 250 to 350 beats per minute. And in the fibrillation, the heartbeat becomes 350 to 600 beats per minute. So the heart is beating real fast. And when it is beating real fast, it is not contracting completely or opening completely. So that is why the amount of blood that is passing through the heart becomes less. It is fluttering. It is not really going this way. So that is creating a problem. In the atrial fibrillation, you see heartbeats are huge. The ECG, if taken at that time, will look like this, where there are several P peaks and they are not really fully peaks, right? They're kind of chaotic signals which are going up only a little. So this can be life-threatening if it moves onto the ventricles, because the ventricles are large and they are the ones that directly push out the blood. Look at this, the ventricular tachycardia. When there are fast, look at the wave that is seen. Instead of the plain wave that was passing, now you see something going round and round. I'll tell you how we found that. But if you do an ECG, or the doctor rather does an ECG on you or on the patient, will see this kind of a very complex QRS wave, okay? Because it has to do with the ventricles. You saw that the QRS wave was responsible for the activity of the ventricles. So it is becoming very complicated. And this is potentially life-threatening, as it can create a lot of problem in the patient. And how is it solved? I will tell you in a while. Well, with medicines and defibrillation, okay? And this is ventricular fibrillation. There you can see a lot of different kinds of circular moving waves. So these waves, if they form in the ventricles of the heart, then it might cause death within minutes. You can see that the ECG now becomes kind of very flat with very chaotic and random spikes in there. And the person can only be saved by an immediate electric current. Okay, so let us look. This is a Holter monitor. So it is nothing but an ECG that is attached to a patient and can continuously take ECGs. Okay, so every line here is a minute. So you can see the heart was beating perfectly, 1, 2, 3, 4 minutes. Something happened in the end of the 5th minute, and something random. You see, things got really bad, And then things started getting chaotic. So that is like ventricular fibrillation. And after another 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 minutes. At the end of the 13 minutes, you know what that means, right? The person has come across death, or whoever had this heart. This is cardiac death or cardiac arrest. And with sudden ventricular fibrillation, the owner of this heart died. How do we save it? How doctors try to treat it? They immediately, if an electric shock is given in a particular way, you cannot just open a wire. There are pads called defibrillation pads, and putting it on the heart, you will see a lot of this medical serials. A lot of you might be seeing in Netflix and otherwise. You will see these kind of machines that should be kept actually in an ideal situation, even in universities and offices. So you can put these pads and administer shock. So it is expected that all these bad waves that you saw will be erased along with the heartbeat. And then a CPR is given where pressure is applied onto the heart of the patient. You might have seen that many times, and in a rhythm, and hoping that the pacemaker cells start to give off the regular beat of the heart. But though the person may be saved at that instant, this high voltage electric shock that is given are sure to burn some tissues. So this tissue damage that is happening will not only make the heart weaker, but may also cause further formation of such waves and further heart attack. Okay? So we need better methods of stopping this defibrillation. So before we go into that, we have to understand why this is happening, how this is happening, how to control such waves. And if you think about the heart, it is opaque. You cannot see what is happening inside. Even if you have a way of looking at it, you will only be able to see the top, the epicardial tissue. And secondly, it will be very costly to get hold of a heart, whether that be a human or of animals. And once VF or ventricular fibrillation occurs, then you cannot revive that heart again, right? So there are some countries which can actually look at it, but ideally you need some models, some laboratory models. Before that, I will quickly show you. This is pictures of the visualizing the electrical activity, that is the waves in cardiac tissue, and you can actually see the waves on top of the heart. These kind of experiments are carried out in Germany, in USA, Canada, as far as I know, maybe in other countries too. But in India, we generally don't look at a real beating heart in a laboratory, though people do observe the hearts in living beings. So what is the mechanism of this tachyarrhythmia? Okay, so we can have mathematical models and laboratory models. Let me quickly show you some mathematical models. So this is, you can see some differential equations, right? The main variable is V. So V here is the potential. So since we are talking about electric currents, this is the kind of a model, Luo-Rudy model, very famous model. I'm not going into the details. There's a Fies-Hugh-Naguma model, again, using the voltage and the V-gate, all voltage models, okay, and membrane potential is also used to model. So these models help us to see how the waves, the plane wave that was going hard, what happened to the wave, how things changed. But as I promised you that I'm going to give you the link with chemistry, the Belousov-Zhabotinsky reaction system also acts as a model for the heart, as it can form different kinds of waveforms as the heart. The waves are not electrical. In this particular case, they are chemical waves, but they have exactly the same qualities, and we can try to understand them to understand the waves of the heart better. So there is a simple experimental setup. So you can mix up the chemicals in a beaker, pour it into a petri dish, and you need to light up because the waves will be light. So from below, you can take a LED lamp. Nowadays, you get these flat LED lamps for the ceiling, right? They're very cheap. You can place your petri dish on that, and you can look at it from the top. If you want to record it, you can use, I use a CCD camera in the lab, but you can simply use a webcam to record the images onto a computer, okay? So let us look at one of the recordings, how it looks. So you see that other than those round, symmetrical waves that we had seen, right? All these spheres. Here you can see that is a spiral wave. So this is a spiral, and if I run it once again, you can see that there are two tips. One of the tip I marked with a red dot, and you can see that the spiral tip rotates around the dot. So kind of that is how a spiral behaves. Not always necessarily, but yes. So spiral waves, this is the busy reaction. This is the actual color, how it looks like. And this is a cell culture of the ventricle, okay? So that is the heart muscles. You can see a spiral. But it's not only in the heart and the busy. Spirals are also formed in cell patterns. Calcium waves in oocytes, okay? This is a wave which is spiral, and this is in the amoeba population. And this is a spiral in neuronal tissue. So what is this amoeba population? Means it is not a single amoeba. It's a colony of amoeba. If you put it in a petri dish, allow the colony to grow, and then reduce the food, what is going to happen is the amoeba is going to arrange themselves like a spiral. So understanding this kind of waves or this kind of pattern is not only going to help us understand the cardiac system, but also all these different kinds of systems. And in the amoeba and the nerve tissue, these spirals are actually very important. They help the organism to survive. Whereas in the heart, it is it to be there. So these are scroll waves, three-dimensional. So we know that the atria is thin, right? So that the waves there could be thought of as spirals, but the rest of the ventricles are thick and it's three-dimensional. So we can have scroll wave. So this is scroll wave in Belousov-Zhabotinsky system. Some other systems other than the heart and the busy, to give something like a scroll, this is not really a scroll, are vortices. Okay, so you might have seen vortex in water when you suddenly open the basin and it goes like this. So that is a vortex. A tornado is a vortex. There can be vortices of air when the aeroplane turbine works. This is basically a cloud, a smoke that is colored, and you can see the vortex there. So basically what happens, you can see here, if I have a round scroll I just showed in the previous, this waves go in. We have cut the front part. It's like a tire that goes in. And to understand better, this is a scroll. You know, everybody knows the scroll of paper, right? So that is a scroll. And if we take thin slices of the scroll, then we will see it is like one spiral stacked over the other. So if you take several spirals and stack them, then you will get a scroll. And the tip of the spirals will make that red line here, which is known as the filament of the scroll. So I'm not going into the details. So we saw chemical waves. What are they? In the heart, we know they are electrical waves giving rise to mechanical contraction. But in the busy reaction, they are chemical waves. So why do they occur? They occur due to an interplay of reaction as well as diffusion. So you remember when I showed you in the beaker, when we were stirring, the chemical, the colors were just going from orange to blue and back to orange. There were no waves. But when I put it in a petri dish without stirring, we started seeing these beautiful waves. So if I write the chemical equation, dc dt, C is any concentration, that is equal to F of C, whatever kinetic part we have. And then with that, I add a term, some flux. So the rate of change of the chemical species or the concentration is equal to kinetic terms, that is the reaction, and along with it, the diffusion. Those who have of you have already studied Fick's law know that for translational diffusion, so if I have a petri dish of water and I put a drop of ink in between, what is going to happen? The ink, the molecules of the ink are going to spread. So that is diffusion, and it gives rise to mixing. Okay, and Fick's law of diffusion says that diffusion is D, the diffusion coefficient, into the gradient of C. So if the C is the concentration. So the kinetic terms, so if I think about a simple reaction, A going to B, then that makes A and B separate. And the diffusion terms is mixing. So it makes A and B mix. So this kind of competition between the separation and the mixing is going to give rise to these beautiful reaction diffusion waves. So this is diffusion in 2 dimensions. The whole equation, I am writing all in terms of partial derivatives now because we have more derivatives in the x and y direction. dc is the diffusion coefficient, right? So this is a very simple model of kinetic model of the Belousov-Zhabotinsky reaction. As I said, it will have numerous steps, but this is a simpler originator model which still has 5 steps, right? You can see the autocatalytic step here. A plus x gives twice x plus twice z, where x is HBRO2. We already know, right? HBRO2 gives rise to HBRO2. So these are the rate equations, and then you have the rate constants where the concentration of the H plus has been input into the rate constants. If we quickly look at x, y, and z and how they change with time, we are doing a computer simulation. Of course, experiments can also be used to show that. You will see that their concentrations kind of oscillate. Okay. Well, of course, the bromate A will not oscillate. A is going to go slowly, it's going to disappear because A is never forming. X is forming again and again. It is getting used up and again form, getting used up and again form. What about Y? Y is also formed again in the system. Z is also formed and also used. So all these that are used up and again formed are going to give you this oscillations. And what is Z? I have written here the cerium. In the case of heroin, it will be the Fe2 plus and Fe3 plus. It will go up and down, and that is the color change that you see. These are oscillating reactions. So what? We did our reactions, we did our simulations. So what did we learn about the heart from there, right? So we learned that the spirals are there in the heart. So these are these waves that are going round and round. And the velocity of the spiral is more than the plane wave. Okay? And that is what is causing the tachycardia or the fast heartbeat. So if you look at this, the contraction of the top and the bottom, since there are the spiral waves in the bottom, it is moving much faster than the top. And if you look here in the bottom panel, the atrial tachycardia, since the atria has spirals, it is moving much faster than the ventricles. So why this happen? Okay. So if you have a plane wave, it is going with a velocity, let's say v. If in the same system you have a wave going with which is concave, then the velocity will be faster than the plane wave. And if it is convex, then the velocity will be slower than the plane wave. So think now of the plane wave moving like that. If it is a straight wave, the curvature is same. Everything will move with same speed. If it is a circular wave, again the curvature is same and everything will move with the same speed, like we saw in the target patterns of the BC. But as soon as there is a spiral, the curvature along this red line is different, right? And the curvature at the tip where the red and the blue meet is 0. It's flat. So the velocity there will be 0. And the velocity is going to change everywhere else, okay? So this is how the spiral has actually different frequencies at different regions. And this gives you different electrical signals. And finally, it's adding up of all the signals. When you have too many spirals, then all these signals add up together. And instead of giving a nice resonating, nice peak, it's going to give you destructive interference. And that's what we see. Things get chaotic and things get flat. And finally, it creates a huge problem. So how these spirals can be formed? Think of a plane wave, okay? That is going slowly. This is the front of the wave in red and the back of the wave in blue. Somehow it's getting cut in the middle, or any portion is getting cut. Now what is going to happen? The wave is not only going to go straight down, it is also starting to move to the right. And this right movement is now, it's kind of a concave, a convex, and that will be slow. Since the convex part is slow, it's going to move slower than the rest of the plane wave. So the plane wave goes much more than this goes, and slowly it is going to curl in and you will get spiral. So think in the heart, we have these plane waves going from the sinoatrial node. If there is a blood clot or a dead tissue in between, then that wave is going to be broken. And the two broken ends are free waves, right? and they will curl in and form spirals as they move. Now, this is how spirals can be formed in the heart. It can also be formed in other methods. One is, suppose a wave is going and there is some weak muscles, it goes slower there. So it can just turn in and form, curl in like that. And another very important thing here I'm showing you. Suppose there is one wave after another coming very fast. So what is going to happen? So suppose this wave is almost going to end, right, at the right of the box. And another wave comes from the other side. So I told you about the rest period or the refractory period, right? So after one wave passes, the system comes down to its rest state. Let me give you another example of rest period to give you an idea. So think about a forest and think about you're sitting in the center and you're starting a wildfire. The fire will burn down the entire forest, right? And the forest is gone. You can think of that as a signal. For another signal to pass through the forest, the trees have to grow. So in that case, the refractory period is decades long, right? At least 10 years, 12 years till the trees grow again. And only then another period, another wildfire, another signal can be passed. So similarly in the heart, it is a few microseconds, but it requires that time to come down to the rest state. It needs to rest. But if the person is very excited, that if a person is very excited, a lot of temper, then what will happen? The heart will beat very fast and one after another wave comes. And if the system does not get the chance to recover, then what is going to happen? The wave will not be a full wave and it can break and it can curl in and form a spiral. So that way also, such a spiral wave can be formed in an otherwise very healthy heart. So these spirals can move around one point as I showed you earlier, or they can drift. And the drifting acts like Doppler effect. You know what is Doppler effect? You all know that when a train comes giving a horn, it seems like the horn frequency is changing as it comes close. And again, it changes, right? But actually the horn is blowing in the same frequency. So similarly, the Doppler effect will change your ECG and make it look like that. So that is known as a very important term in biology or medical science, torsidis, depointis, and this is basically polymorphic tachycardia. Different kinds of tachycardia are there. And now, one spiral, we saw how it formed. Now, if the spiral breaks up and forms many spirals, that is when you are going to get fibrillation. This turbulent state or chaotic state is ventricular fibrillation, when the patient requires immediate attention of a few minutes. So tabulating it in short, a stable spiral wave will give you, in the ECG, it will look like that. It's known as monomorphic ventricular tachycardia. As soon as it starts moving, you will get the torsioids depointis, right? And it's polymorphic ventricular tachycardia. It starts moving without any particular direction, very chaotically. Things start getting chaotic. And when there is spiral breakup, you get ventricular fibrillation. That is the worst of the lot, right? So now we need to understand these phenomena. So this is actual pictures of a heart where you can see it's a rabbit heart and you can see spiral waves on the top of the heart, on the epicardium of the heart, okay? And it is only a matter of guess. The scientists can only guess that maybe the wave is in this form or is it in that form by looking at this, but they do not actually see what is happening inside. So, but in the chemical case, in the BZ reaction, we will be able to see the waves. So, we see the waves in our reaction. Now the question is, how can we control these waves? First, let us think about the chemical waves. So, dC dt is equal to Fc, the kinetic term, as well as the diffusion term. So, how can we change the kinetic term? If we change the concentration of species, the kinetic terms will change, right? And if we change the flux, how can we change fluxes? Now think of chemical reaction. We saw that there are ions, right? Some are positively charged, some are negatively charged. So what if we apply electric field? Then the positive ions will go to the negative electrode and the negative will go to the positive. So that will create another flux. What if we apply thermal gradient? What will happen? Let's quickly have a look. Okay, these are just equations. How the equation, the flux changes, I'm not showing you. What will happen under thermal gradient? There are heavy, larger particles and smaller, lighter particles. what will happen if I apply a hot heat on one side and pull it in the other side? What will happen is the larger particles will move towards the cold end and the lighter particles will move towards the hot end. So another flux will be created. And by using this kind of systems, we have been able to show in the BZ reaction, a spiral in the beginning you saw was rotating around the spot. And here you see how it is moving towards the hot end, right? The spiral is no longer fixed at one position. It is slowly moving towards the hot end. Similarly, in the lower picture here, you can see that it moves towards the positive end if we apply electric current, the spiral will move towards the positive electron. Also, magnetic field can be used in reaction diffusion systems to give rise to beautiful patterns and noise. So these concepts I'm not going through in details, but it is possible. Okay. Of course, in the case of magnetic field, we will need a dipole, right? Something has to be magnetically active, an isotropy. Again, I told you that changing the concentration. So here is a very simple example where I am keeping the malonic acid and sodium bromate in the first two are same, but we are decreasing the sulfuric acid. So we see that the frequency of the waves or the wavelength, the frequency decreases, the wavelength increases. And if we keep in the first and the third, the sulfuric acid and the malonic acid are same, and sodium bromate has been decreased. Again, the frequency changes. So a lot of things can be done and a lot of things can be looked at. If we go back to the heart, how is it going to help? Well, we know that the sodium comes in to excite the atria, right? The heart cell. So if we can apply any such medicine that is going to block the sodium channel, then it can stop the heart from exciting so much and slow down the heart waves. Indeed so, tetrodotoxin is one such, TTX is one such chemical that is a sodium channel blocker and is used to bring down the heartbeat, as you can see here. Okay. So this is a simple example where I have put a different, this is not a Belousov-Zhabotinsky system. This is a CO, carbon monoxide and oxygen on platinum. So this is another Nobel Prize winning work by Professor Gerard Ertl, where they look at surface phenomena. Okay, you can have a look at his work, very different kinds of work. So we can attach these waves to obstacles and we can see how that means anything in the heart. And we can detach these by using electric fields, and a lot more experiments can be done, and that can be matched to what would happen in the cardiac system. Okay. So now, with all our understanding using models, chemical models as well as mathematical models, we understand about the heart, about the system, about the waves. But to go back to the heart, to use it into actual medicine, you have to go back. A technological leap is required. We as scientists can only find and understand these things, but to use it will require a bridge. And it is for the next generation, people like you, to actually bridge that gap. Okay? Can we use these techniques in the real living system? To end with, I will just go through a few more patterns and tell you how chemistry is used. I'm not going into details, but just showing you some pictures. This is some other systems. These are hydrothermal vents, A. B is a brinicle. So these are all happening under the sea. Hydrothermal vents are vents from the deep of the center of the earth where warm waters flow, and it has a completely different ecology from anything up on the ocean surface or anything on the earth. These are brinicles, means they are salt water comes inside and forms icicles like that. These are soda straw, like in the caves, and these are black smokers. So these are very important phenomena down in the oceans and can be understood by chemistry in the form of chemical gardens. You see, they look beautiful. You basically use an anion, a silicate or aluminate as the solution, and in it you put a seed of a metal salt. This is very simple. You can also do it in your laboratory. Have a look at chemical gardens. They are beautiful to look at, and they actually give you some interesting phenomena, the understanding of these phenomena. Okay, I'm not going through the chemistry. We have just a few more minutes. This is one example where using an agarose bead, you can make a very nice tube with an ending that is kind of crooked, right? So these are nanotubes that can be controlled synthesis. We did it in the laboratory. And this is not by our group, some other group. In science, you see how beautiful structures they have made. It is a controlled growth using chemical and electricity also. They can, the colors are not real in this case. The colors have been put just for the aesthetic pleasing sense, but you can see just like you see all this fondant art in the cake people do with fondants, right? So similarly can be done at a microscopic or rather submicroscopic level using chemicals. This is another way where optical control has been used to make these tubes, and you can understand what beautiful you can actually make the whole lot of things using this, using laser, right? You can make different kinds of maybe reaction chambers. You can make channels through which you can send medicine, and so many other things can be done. Another simple example of a chemical reaction, this is the laser gang ring formed with lead iodide. It's just precipitation. Again, you can do it in the laboratory. Ki in PbNO3 twice. And it helps us understanding geological phenomena in huge scale. These are laser gang rings that are found in rocks, just like rings in plants, in big trees, right? Wood. Similarly, these kind of rings are found in nature and can be understood by simple chemical experiments. Self-organization can also occur at the molecular level. As you know, the DNA, double helix, RNA, monohelix, and these shapes and these molecules are so important to pass on the genetic information, right? Understanding them is very vital to the understanding of life. And simply look at our skin. It is a bilayer of lipids. How do we use it? Simplest case. Without knowing, we used to use, and now we know. What is soap? It is a long chain hydrophobic end and a tiny hydrophobic end. What happens to the hydrophilic end as soon as we put water? It forms micelle. Exactly. And since this is hydrophobic, if you have oil and grease, it will be trapped in the middle, and you can clean your clothes with this. These are some other beautiful patterns which are known as fractals, means they repeated patterns. These are snowflakes. This is a fern and a cauliflower. Of course, you might have wondered as a child, why does breaking a cauliflower still make it look like a cauliflower? The smaller we go. And these here are some precipitation patterns of silica tubes in the laboratory. This accidentally happened. The color, of course, was not green or yellow. We just put the colors to make it look like what we see in nature. And if you have noticed carefully, the lungs from the trachea to the bronchi, if you just take away the muscles and all, you will see it looks like exactly like the tree. And that is what nature is. The same kind of system is used in different organisms, different systems to do similar kind of work. The tree branches like that to take up water and nutrients. The lungs branch like that to take similar, it's similar but completely dissimilar again, right? And this is what a fractal is. All the shapes I showed you in the end is fractal. So you take a triangle, you cut out a small triangle in between, and you continue doing that again and again. And you end up with a beautiful triangle like that. One more important, interesting thing here is the Koch snowflake. You take a triangle, take the middle 1/3 of each side and make a small angle. You get a star. Then you continue doing that to each of these segments, and you end up with something that looks like a snowflake. This is known as a Koch snowflake. And this is a picture that you might have seen or not seen, rather. It's something that's worthwhile to be seen. It's known as the Mandelbrot set. We zoom in here. This is X1. Zoom in S6. You see it's exactly same. X100 again looks the same. And X2000 it still looks the same. So these are marvelous fractal patterns. And how do we use it? The chemists use it very intelligently for drug delivery. This kind of a fractal geometry with lot of hydrophilic outside ends and something to capture the drug can be used that can be sent into the body, and it is going to deliver the drug exactly where we want it. It is also used for electronic applications. And interestingly, liquid crystals, are used everywhere, right? In your phone, in the TVs. And chemists take inspiration from this kind of mosaic viruses to form liquid crystals, which are otherwise not very easy to form. So there are so many ways that we understand from nature, and we try to understand nature. We use it in our advancement of science, right? So if you look carefully and think deeply, you will understand that a tree branching from the trunks to the twigs has the same fractal geometry as our lungs, from trachea to the bronchi. From the human heart, you have the spirals. The galaxies are also spirals, right? From geology to chemistry, everything, there seems to be a tune that binds us together. So in a world that is very chaotic and otherwise very dissimilar, there is a similarity that is underlying everything. So chemistry is not separate from all these sciences. And as you go up to higher studies, you will see that the separation between the subjects actually dissolve, and everything is one big understanding of nature and science. So thank you so much for your attention. And this is my email ID. I would very much like you to contact me if you have any questions about the chemistry, about the equations, about the subject, or anything else that you might like to know. So thank you for your attention. I would really like to hear some questions.
Thank you, madam, for your enthralling presentation. Is there any question from the participants?
You can raise your hand.
Please listen to ma'am what is saying. Any question?
So if you see, this is where you raise your hand. Here, raise hand like this. If you have any questions. No? Maybe they are shy. Then please write in the YouTube forum, Professor Mitra. You should also share it with us, because if they ask questions there, maybe we can reply there also. And you please feel free to share. Okay, students? Okay, some... Okay. Stop presenting.
No, madam, I don't think that there is any question, even in the YouTube chat box.
Yeah, it's fine. Maybe they will ask later on if they're interested.
Yes. So thank you, ma'am. What I personally feel that it has been a wonderful learning experience for the teacher participants also. That how can we make teaching more interesting, just like relating science to the mother nature. It is a wonderful presentation, ma'am. Wonderful learning experience for all of us. Thank you very much, ma'am.
Thank you. I think there is a question by Sudeep Datta.
Yes.
You wanted to know about hydrothermal vents. Yes, what did you want? Basically, hydrothermal vents are, they occur due to, because it tries to basically take the heat from deep within the Earth's core into the depths of the ocean. So in that form, what happens? There are some areas very deep in the ocean where there is no light or anything. So there the temperature rises and an entire ecology forms there, ecosystem. So in order to understand that, what chemists do is we try to just form this kind of tube. So these vents are formed. So what is the nature of these vents? So chemical gardens gives us an idea. So you can just take yes, Sudeep Datta, you can speak maybe?
Yes, ma'am.
Yeah. Yes, I would like to hear your question.
Yes, ma'am. I say about hydrothermal vents. What is the hydrothermal vents? And I see some documentary. This
Yeah,
type of. Yes, ma'am.
yeah,
So,
yeah. Have a look, and have a look at chemical gardens also next time, and you will see how easy they are to do. So if you get your hand on one of these chemicals, you can try to make them. Okay.
yes, ma'am. Thank you.
Any more questions from the participants?
So
No more question, ma'am.
yeah, thank you.
Thank you, ma'am. Thank you.
Thank you so much.
It was a wonderful presentation, ma'am.
Thank you so much for the opportunity. I hope people have.
Nice to meet you, ma'am, after a long time. Please
Yeah,
take
after a
care.
long time. Yeah, you all too.
Yes, ma'am.
Thank
I
you.
would now like to invite Professor Joyashree Shaduka, madam, to address the august audience about the workshop, about the norms of the workshop. Joyashree, ma'am, please. Yes, yes.
Good afternoon. Greetings of the day, dear participants. We are on the very first day of 3-day long national web workshop on chemistry orientation for UG and PG students, organized by Association of Chemistry Teachers and Government General Degree College, Singur, Hubli, in association with Rani Rashmani Green University. So the basic motto of this workshop is to enlighten and illuminate you students from the very basic core who deliberately miss regular interactive practical classes, interactive college learning session in this pandemic scenario. So our basic goal is for the enlightenment of students. I am especially thankful to the organizing committee members, advisory board members, especially to the convener of today's program, Dr. A.K. Mitra, our eminent speakers who have devoted their considerable time for the upbringing of young chemistry learners, President of Association of Chemistry Teachers, Professor B. Pare, General Secretary of Association of Chemistry Teachers, Professor D.V. Prabhu, Principal, Government General Degree College, Singur, Professor S. Chakraborty, Vice Chancellor, Rani Rashmani Green University, Professor Ashutosh Ghosh, for planning such a nice workshop on the virtual platform, even in this pandemic scenario. But all our efforts will just go in vain unless and until you people respond to it, you get actively involved in this workshop to get its maximum benefit. So it is not a mere lecture session. It is a workshop where your active participation is always appreciated. So each and every day, we will start our workshop program, sir, at 3 p.m. At the end of every session, you will have assignment link in your chat box. Please go through the entire session with attention, and at the end of each session, click on the assignment link. You will have several multiple choice type questions and several subjective questions. Go through these questions carefully, answer it appropriately, and submit those assignments within 10 p.m. of each and every day. Unless and until you submit it, you will not have your workshop completion e-certificate, and after 10 p.m., no submission will be entertained. So please be attentive in this during the entire workshop session, and our scope is limited in the Google Meet platform. So if you fail to join through Google Meet link, please go to the YouTube link and follow this program in the YouTube live streaming. Hopefully, you will enjoy the entire session and will get very much benefited from it. So let us move together for this 3 days. Thanking you all. Over to
Okay,
you.
thank you, ma'am. Thank you. Actually, the tomorrow's session will start from 3 p.m. at sharply. and it will continue around 5:45 to 6 p.m. So if you don't get chance to join via Google Meet, since there are too many participants, you may join us with the help of YouTube live streaming. And you will get all the assignment link both in Google Meet chat box as well as in YouTube chat box. And at the last day, you will be given assignment link as well as feedback form link. And after the overall consideration, you will be awarded an e-certificate. Thank you. Let us close this event for today. Hope we will meet again tomorrow. Thank you all.
Thank you, sir.
Thank you. Thank you.